decisions.
That's a little slow side.
No, paper is
Trying to catch up with daylight savings.
all the time.
No, not for all the courses.
Okay, so let's, well, just a few minutes before we get started, and let me just mention, once again, let me remind on the update for everything. Next Friday is our last student seminar. All right, next Friday's the last one, and Alisea and Shoba will be presenting next Friday. And then we'll have our holiday, our time off, getting ready for the holiday break after that. We'll pick it up again in the spring. So for today, there are two speakers. Michael is here, Michael Taff is here, Alta Bailey should be here soon. She sent me her title. So, topics, I'll just let the speakers go ahead and present their topics. So why don't you go ahead and start, Mike?
All right, good afternoon.
Good morning.
Good morning.
Good morning.
All right. Is it morning?
Yes.
Sorry, I'm ahead of myself. So my name is Michael Taff. I'm a master's candidate in chemical engineering. Actually scheduled to graduate next semester. Praying all goes well.
Don't you already have a job?
I do have a job. I'll be working for Georgia Pacific as a process engineer and entry-level engineer in Charlotte. So the sooner I get out of here, start work. But so today I'm going to talk to you about what my research has been involved with, and this is kind of the first chapter, so to speak, of my research. I'm currently working on the second chapter, but when I get to future work, I'll kind of tell you guys about that. So the title of my thesis is a comprehensive investigation of the absorption of copper on annotates and rutile titanium dioxide surfaces. And this is a density functional theory-based study. So what I did actually, I just presented this work recently in Raleigh. So this is kind of a condensed form of my poster. And so, as I said before, I'm studying titanium dioxide, and for I don't know if you guys are familiar with methanol steam reforming or converting alcohols into hydrogen fuel, but this is a study of that, a theoretical study of that process. And so I found that titanium dioxide was a complementary surface for this type of work, in which copper is absorbed to the surface. And despite many experimental and theoretical catalytic studies, there are questions about the interaction between the metal and the oxide. And so what I hope to do is kind of shed light on that. And I'll get to the findings and everything later. So the motivation for this work is to find environmentally friendly ways to move from fossil fuels into green energy. One of the promising technologies for doing that type of thing is the production of electrical power from fuel cells. And one of the popular fuel cells are the polymer electrolyte membrane fuel cells. But fuel cells require hydrogen as a fuel, so alcohols are a hydrogen-rich source. The process of steam reforming converts the alcohols to hydrogen via catalytic surface reactions, where the metal copper is supported by an oxide. And so below are the three reactions involved in the reforming process. The number one reaction is the methanol steam reforming reaction, where methanol alcohol and water are introduced into the system at a certain temperature, and At the end of that process, you are left with carbon dioxide and hydrogen. A side reaction is the methanol decomposition reaction, in which methanol is decomposed into carbon monoxide and hydrogen. And another side reaction that you can get hydrogen from is the water-gas shift reaction, the last reaction. And carbon monoxide and water react with each other to form carbon dioxide and hydrogen. So titanium dioxide has been researched extensively for many applications. It's most commonly found in nature as annotates and rutile morphologies, with annotates 101 and rutile 110 being the most stable surfaces according to literature. In catalytic applications, titanium dioxide acts as a support. So when the metal is introduced to the surface, it's dispersed on the surface. The support kind of stabilizes those particles on the surface. And so, like I said, to understand that molecular relationship, we're going to use a quantum level approach. And quantum mechanics is ideal for those intrinsic details that otherwise experimentally you won't be able to find out. Dr. Kavadi did an extensive review of quantum mechanics and Densification, functional theory, and all those things. And so I'm going to skip all of that.
A question, on the surfaces that you're giving numbers 001, et cetera, 101, can you control which surface is exposed?
Experimentally, you cannot. So that's why, we're using theoretical approach. At some point, we hope the science and the technology the gap closes. And so if that becomes possible, then this type of work allows you to tune the capabilities of those catalysts and get better improved catalytic conversion and things like that. Right now, no, experimentally, you can't, get the exact.
Or is it sort of a random orientation?
Yeah, it's random. You get a multitude. Most common are annotates 101 and rutile 110 because they're the most stable. So they show up the most. What it uses is electron scanning microscopes where they scan the material, and that's how they can tell which surface is there. So my method for studying the system is a computational approach. And the computational science is going to describe the properties of matter based on fundamental equations like the Schrodinger equation, which solves the wave equation. And so that equation basically tells you where electrons are in space and how they move and how they migrate and how they facilitate reactions and bonding between molecules. Some of the properties that can be described in computational approaches are structural properties, vibrational, magnetic, electronic, and optical properties. And so the ideal result of running these type of calculations is to get the structures in their ground state. That means that they are their lowest energy state. Because if you have excited state atoms, then you can't control them. And you'll see one of my surfaces has a very high energy, and it led to the deterioration of my copper molecules. So to generate my clusters, I generated different cluster sizes, ranging from 3 to 23. I chose these different numbers based upon what they call magic numbers. And these magic numbers are the most stable known configurations of these copper clusters. And so I ran these energy calculations on these clusters, and I found that copper 7, this pentagonal shaped bi-pyramid, we have a pyramid on top and bottom, was the most stable configuration. And so I decided to proceed with that model for further studies. I also could have chose other copper sizes to study those type of systems, but the larger the clusters, the more atoms you add to a system, it becomes computationally expensive. So we're running these calculations on supercomputers, and even these simple models take a couple of days just to generate results. So, you know, you're talking about orders of magnitude of time, the more atoms you introduce into a system. So not only because of its stability was copper 7 chosen, but also because of the size. So to begin building our, what we call slabs, so our outside surface it begins with these are unit cells of rutile and anatase. So we replicate these unit cells several times. I won't go into the nitty-gritty, but we develop these large slab models, and then we cut the planes based upon existing research and what the surfaces look like. So we cut it down to this is a 101 surface. We cut it down to this 4 layer, and the layers are numbered based upon these gray atoms are titanium, and the red atoms are oxygen. And so what I do is I freeze the bottom layers, and I allow the top layer to kind of move and relax and find its optimal space, optimal locations in space. And once it gets to its ground state, then I can proceed with introducing that cluster into the surface. So when you think about these type of models, we're using periodic boundary conditions. So these slabs or surfaces theoretically run infinitely. And so they are separated by about 15 angstroms of vacuum space. And so when the copper comes in, it goes in here. And when you submit the calculations, and we use a program called Quantum Expresso for electronic structural calculation, it migrates down onto that surface and interacts with the oxygens on that top layer. And so what you'll see is, depending on the stability of that surface, how the copper absorbs geometrically, and you get energy information out of that as well. So what we do next, we scan the surface with the copper 7 model, and we put this model in different orientations on each surface, on different spots, laterally and like perpendicularly, just different angles, and try to find the best absorbing pattern for that copper 7. We did that for each surface, anatase 001, 101, R100, or R110. And we take these coordinates, and these coordinates are XYZ coordinates, they're spatial coordinates, and we put them into that quantum expresso program. Like I said, it runs the absorbing reaction, and then it outputs the geometry and outputs energy information of that absorption relationship. And so from that, you get a couple of things. You get geometrical information as far as, okay, what does the model look like as it is absorbed onto the surface, what you see here. And so we began with the cluster looking like I said, a pentagonal bipyramid shape. And as it's absorbed, we have these planar geometries on anatase, on rutile 100, which is shown to be very high energy. The cluster disintegrates. And so if you were only looking at relaxation energy, you would think, hey man, this R100 surface is really stable. Like maybe, you know, it's a more attractive surface for absorbing copper particles. But when you visualize these structures and complexes, you can see exactly not only its behavior as it approaches the surface, but guess, final absorbing geometries. And so rutile 110 being a really high, the most stable, one of the most stable geometries, the cluster actually remained intact. So down the line, what we want to do is we want to go into mechanisms of methanol reforming. And so we think this planar geometry will be a lot cleaner and more approachable for the methanol species to attack on the surface here. But we're currently in process of working through that. So from that data, we were able to show that the absorption geometry of copper 7 on anatase is most favorable. Additionally, the preferred absorption geometry for copper 7 is a clean aromatic-like square planar base and triangular planar surface. Also, copper 7 clusters undergo significant structural changes when they are absorbed on the titanium surfaces, as I showed with the rutile 100. Anatase 101 and rutile 110 are found to be the most stable complexes, and that's in agreement with the surface energy data that exists in the literature. Also, rutile 100 surface is highly unstable, and anatase surfaces are more stable than rutile. So these models provide the insight into the structural profile of copper cluster absorption on titanium, which can provide atomic level details on how tuning particle size could improve catalytic conversion efficiency. So in the future, I want to determine what the mechanism for methanol decomposition on these clusters is. Right now we know that there are a couple of pathways that exist that begin with methanol and its subsequent dehydrogenation to carbon monoxide or carbon dioxide. We preferably would like to have a carbon dioxide product, because the carbon monoxide product poisons the anode and the electrolytic membrane. And so it's also it's not environmentally friendly either. So if we can redirect our pathway towards carbon dioxide, that would be really significant. And but currently most pathways lead to carbon monoxide. But we also saw that on copper, this carbon monoxide molecule absorbs weakly. So the fouling or the deactivation of the catalyst might not be a problem. So that's it. These are my references. And thank you.
Mike, I have a question for you. So, TiO2, you gotta mine it, and then you gotta purify it, I think, sulfuric acid, there's a sulfur approach, and then there's a, I forget what the other approach, chlorinated approach to get it pure. But even when you get it pure, there's still residual surface issues with each one of them. Can you take that into account? You understand what I'm asking?
Where you want to control what surfaces you get?
Well, I'm saying that, even pure TiO2, it's already gone through a process to get it to pure TiO2. And so there's some residual effects of whatever process it has.
Okay.
Whether it's a sulfonated process or chlorinated process. And, how will that impact the absorption of the copper into the matrix is what I'm asking.
From what I read, it definitely impacts.
It does or does not?
It does.
It does, okay.
Yeah, the processing, the pre-processing definitely has an effect. You ideally would want a pure titanium dioxide surface. Theoretically, we assume that it's pure.
Pure, okay.
But experimentally, it will not be.
Yes.
And that will have a considerable effect. But we do not.
But your model doesn't take that in. Okay.
It's like the ideal
Gotcha.
situation.
I understand. Okay.
Yes, sir.
Thanks.
In that case where the surface was not stable, what do you, would you expect to be the consequences in a real situation? Does that mean it's going to corrode faster, or what does that mean in terms of a physical result?
So the physical result is that not necessarily corrosion, it would bind weakly. So you may not even, you can't control the outcome. So whether if you're trying to get in a certain product, you may not even, the reaction might not proceed because the surface is in such disarray. And so, there are a few consequences for that. But, deactivation might be a problem, but I'm thinking that you won't even get to the point of activation at all. So deactivation is kind of a long shot because the callus won't function in the way it's intended to.
Any other questions? Okay, thank you, Michael. Our second speaker for today is Alta.
Mike, did you load this on?
Yeah, USB drive. You can just close that.
Do you need any assistance with the computers? I can get Carter in here if you need it.
I just need to tell it to use my computer. Oh, there you are. It says your name. You walked in.
Yeah. Who's bottle of water?
But it's not open. It's not like it. Not used to that one. These the ones that activate.
I got that DA.
Yeah, this is a little different.
Oh, this is cool.
Yeah, it's possible.
Oh, it's cool. I was just using my.
Okay.
I was just using my. So good. Yeah, I had to make sure it was still before. So good morning. Good morning, everyone. My name is Alta Bailey, and today I will be presenting to you sort of a two-part topic. So this is basically what I'm doing for my thesis here. And this is in conjunction with Oak Ridge National Laboratory in Knoxville, Tennessee. So today I'll be talking to you about the effect of fluid chemistry on nanoparticle delivery for densification and binder jetting. So that is a very long title, and I'm pretty sure a lot of you may not even know what binder jetting is, but this is in the field of additive manufacturing. So because you may not know what binder jetting is, we'll start there. Everyone, give me time to record my name. All right, okay, I'm gonna keep going. So binder jetting, so let's first start with how it works. And so binder jetting is basically, it's based off of the principle of an inkjet printer. And so what you see here in this photo, wish I had a pointer, but what you see in the photo here, thought I could. Now you guys don't see the cursor.
You can maybe move your mouse around?
Yeah, I did, but it doesn't, my computer is showing something different here. Just for right now, I'll do this. So what you see in this photo is basically a schematic of how binder jetting works. And so you have two sides in a printer, right? So you have a feed side and then you have a build platform. The build platform is where you're building your components. So let's say we were building a screw, a nail, a wing for an airplane, whatever, it will be built on this side. So the concept behind additive manufacturing is that you're constantly building something layer by layer. So you're depositing material layer by layer. So the thing about additive manufacturing is it's different from its subtractive counterparts in the sense that subtractive manufacturing is classically thought to be like milling, or if I'm using like an injection molding type technique, etc. And so binder jetting is additive, where we're doing layer by layer with building. And so how this works is that I have a metal powder or a ceramic powder or some type of polymer powder on my feed side. And so as I constantly build layer by layer, this side will advance upward. And so what happens is this roller will take and spread a thin layer of powder onto the build platform surface here, and then my inkjet print head will selectively deposit my binder onto areas that have been sliced via a computer program like CAD to give me whatever that layer is. And so, as you can imagine, it can get very intricate and very detailed. And so, depending on your build platform volume, this can determine like the size of your part. So some of these inkjet printers are very small, and some of these binder jet printers are very large. So as the binder is selectively deposited, once that happens, a lamp comes behind it and slightly dries it, and then the build platform advances downward. And then you have a new layer of powder that's spread on top, and then the process continues. And this little photo here is basically showing you where the gray particles represent your metal particles, and the blue particles represent your binder, which is saturating these metal particles. Okay, so now that we got that out of the way, any questions? Okay, cool, let's keep going. So once you go through that process of building your actual part, it's followed by a curing step, a depowdering step, sintering, and then infiltration. And so your curing step basically is a step that is used in you cure in a low temperature furnace to dry the solvent out of your binder. So your binder is a combination of a polymer, some type of surfactant for dispersion, and other chemicals that kind of help hold these metal particles together. So once you cure, you remove your part out of a low temperature oven. At this point, it's very fragile. Like I wouldn't be able to use it for an application. If I drop it, it's probably broken, etc. And so, but I do have to depowder it. So the depowdering step is kind of like what an architect will use to depowder some type, not architect, but a mine just went blank. Archaeologist, there we go. What an archaeologist would use to remove debris from whatever archaeological artifact that they're trying to visibly see. So that's kind of what happens in the depowdering step. After your depowdering step, you follow up with a sintering step. And so sintering, what you will see here, happens in a high temperature furnace. And so what happens during the sintering step is, let me come back to my schematic here. I need to like touch and feel and see, so hopefully you guys don't mind. So within the sintering step, so this is where we cured, we depowdered, and now we're setting up for sintering and infiltration, which is like a combination step. So before I can actually sinter, which is done in a high temperature furnace, I have to do an infiltration step. And so currently with binder jetting, the problem is that the parts that I produce, they are 60% dense. So I have 40% void or unfilled space. And so my part doesn't have the mechanical properties that it needs, etc. And so what happens now is that we have to create material that is like an alloy. And so this could be any type of metal that has a higher melting point than bronze, because bronze is what we currently use for infiltration. So we will set bronze up underneath the parts that we actually want. And so during the sintering step, this bronze is wicked in through capillary forces or capillary action. And that bronze fills that 40% void space during the sintering step in the high temperature furnace. And then once that happens, as you can see a color change here, the part comes out, and then we have to cut off these runners, which is basically what we use for the infiltration step, and then we have our final part. So at this point, your part now is about 100% dense, 99 to 100% dense. But it doesn't have the full mechanical properties of, let's say, stainless steel, because now it's stainless steel infiltrated with bronze. Dr. Nicely, you're giving me, I'm lost, look.
No, I'm just amazed it's 90% dense. How much density did you say?
So with binder jetting right now, because we're using powders, you end up with a 60% dense part. So you have 40% void space that you need to fill. And so we fill it with bronze via the infiltration route.
But you had a really high number at first, right? 90?
No.
Oh, no, 60, okay. I
60.
I didn't hear it right, okay.
And then 40% is unfilled or void.
Oh, okay.
Okay. Ladies and gentlemen, I'd like to welcome you to my presentation. All right. So, what this is actually called in the world of additive manufacturing is a packing factor. So when I was talking about density, we call it a packing factor. So of 60%. So like I said, it's fully dense, or not fully dense at this point. But one way that I can reach full density is if I sinter it to full density. And sintering is just a process to where you give me a look. Did I finish you? Okay. It was all in fun. It was all in fun and games. It's cool. So I can sinter to full density if I leave it in the oven for a long period of time or add excessive heat. But what happens is I have an unpredictable geometry and warping, and so basically if I need this component to be this shape for me to use, if I sinter it to full density, to 100% density, it shrinks, it warps. I can't predict what the geometry is going to end up being. Some of these spins may not be to the accuracy that I need them to be, or shape, etc. So I can't use that part. So that's why we have to do infiltration. All right. So let's keep going. So to reach full density and avoid shrinkage, the goal or idea here is to be able to use some other particle to fill the empty space. And so, I really hate that I can't touch this. Sorry. That's right, it would have been a problem. So what you end up having when you have the powder bed, so that feed materials, you have a monodispersed particle size distribution. So you might use 60 micrometers, 80 micrometers, 70 micrometers in terms of the size of your powder. And so this is why you end up with your 60% density, because you have these areas here that are not filled, this void space. And so the goal is, if we can increase the packing factor before we sinter, cure, and all that stuff, then we can have a higher density at the end. It may not need to do the infiltration. And so what we want to do is create a bimodal distribution for the particle sizes. And so that's where the nanoparticles come in. So we go from a mono-size distribution to a bimodal distribution to increase the packing factor. And so currently, via literature and experimentation, it was done back in like the 80s. The maximum packing factor that you should be able to reach right now is 0.868.
So you have 2 minutes, according to the clock.
Okay, 2 minutes. Let me speed it up. So like I said, the end goal for binder jetting is for me to be able to put nanoparticles within the binder, and whenever I'm selectively depositing that binder, those nanoparticles will fill that void space, increasing my packing factor, increasing my final density so that I don't have to do back infiltration with a secondary material, right? So actually what I'm going to do is I'm going to skip this first part right here, and I'm going to go to the second part. I'll give you a summary. So the first part was basically where we want to see what happens with nanoparticles and the binder, and see if we could take and change the steps. So where we could take nanoparticles and put them directly in the binder and put it on top of a centered part, and then recenter it to see if we increase our density. It didn't work because we couldn't figure out where the nanoparticles went. So this led to the second attempt. And so this is what I did basically this summer at ORNL, is we changed the methodology. And so we wanted to be more analogous or simulate what actually happens in the binder jetting. And so we decided to change the way we deposit nanoparticles into the powder. And so this time around, we used copper nanoparticles, which would give us a color differentiation between stainless steel particles. And so we took copper nanoparticles and mixed them with binder, and then mixed it with the stainless steel nanoparticles. And then we casted it, cured it in a low temperature oven, and then sintered it. Using this sintering schedule, and so this is just basically our heating schedule. You know, this temperature for that amount of time. So this takes about 7.5 hours to sinter. Not to build. Additive manufacturing is still pretty fast, but this is like post-processing. So what we ended up getting is that we were able to now see the visible location of the nanoparticles, or where they went. And you can see this by the shading, the color difference here with these pictures. And so basically we did a 4%, 7%, 10%, 20%, 40%, and 70% particle loading mixture to see if we can have a difference of where the nanoparticles went. And so at 70% loaded, it appears to be fully dense, but this is just a selected image for SEM, right? And so we found that the nanocopper acts as a sintering aid. And so sintering is basically where you have these larger metal particles that are forming these necks in the presence of a high temperature. So they're forming these necks where they're coming together, and so your grain boundary is shifting and changing. So also, just to give you a graphical or a visual representation of the casting process. So this is what a binder jetting printer would deliver as an output. It's basically a perfectly shaped bar, really no errors, and this was additively manufactured, layer by layer. This is what I did via a hand packing method to simulate it, relatively close. And then, but this is without the nanoparticles in it. This is when I put the nanoparticles in it. I ended up with this, and this is just only after counting. So as you can see here, when we were talking about density, this one, based off from the printer, is only 60% dense. It's hard to believe because it looks fairly dense. This, where we put the nanoparticles in it, increased the density here. You see a lot more pores, it expanded outside of the geometry we wanted, etc. So that was a problem. So some of the macrographs of some of the mounted samples with the percentages that I gave you here show that you had an increase in porosity as we input more nanoparticles into that matrix. So the theory that we had before didn't necessarily pan out, and so going back to the drawing board, we came up with this theory, the bound binder theory is what we call it, where you have the nanoparticles preventing the venting step. So during curing, you have to have the solvent that evaporates out. So with the high amount of nanoparticles that we put into the system, it prevented the venting of the solvent in the binder. And so that's what caused these particles to move out as well, which is what you saw in the previous picture. So what did we learn here? So the conclusion is that nanoparticles do work very well in terms of their packing, because it did increase the packing factor. But we need a solution to the off-gassing before we try to go and actually put nanoparticles into the binder, which is selectively deposited into the particles. And full density is potentially achievable by filling that void space. And so the work that's going on now, which is what I'm working on, is we're trying to determine the nanocopper's effect on binder. As you know, when you're dealing with nanoparticles, they have a higher surface area, and so that gives you more reaction sites. So there could be some type of reaction that's occurring between the binder and all of its components and the nanocopper. Also, we're going to explore the use of other metal nanoparticles, because copper could be the culprit here. So we're going to go with stainless steel nanoparticles or iron or whatever the case may be. And then see if we can produce a single alloy fully dense material. And then also investigating different binders and curing cycles. There's literature that shows the effect of curing cycles on what happens to your final part. So that's like changing the temperature or how long you keep it there. So that was that kind of step graph that I showed you all. And then looking at determining an optimum void fill fraction, nanoparticle to binder ratio to eliminate or reduce that fluffing that we saw. And then vary the binder solvent, since we have to eliminate this off-gassing phenomenon. If you would like any questions, but if you like more information, the first part that I didn't actually go through is presented in a paper here in the American Journal of Engineering and Applied Sciences. And the second part that I did kind of run through is presented here in the conference proceeding. And it is a manuscript. So 2 publishings. I like flew through that, but okay.
I have a question. Does it matter what material the nanoparticles are made out of? I mean, did you try more than one
metal.
Type of material, yeah.
So the first experiment I didn't go through, we did stainless steel particles to stainless steel nanoparticles. And the thing is, the method had an issue in the fact that we used the same material. We couldn't see exactly where the nanoparticles went when we went back and did imaging. And so we didn't know if the nanoparticles, because when you reduce a material down to that length scale, you also change the properties in terms of the visible light properties. You also change the properties of its melting point, etc. So we didn't know where they went. But we are investigating the use of different nanoparticles because, like I said, we didn't know if, with the second attempt, if the nanocopper was causing a reaction with something in the binder. And so because we're working with X1, which is the company that makes these binder jets, these binder jet printers, we were using their binder, and they have some proprietary things, like in terms of the polymer that they use is proprietary, so we don't know. But we do know what the solvent is in it. And so we're doing some FTIR and UV-Vis experimentation to see if the nanocopper is causing any changes in that solvent. And right now what we know is that copper and that solvent is incompatible. But we're trying to see exactly why, like what happens.
I think in one of your slides you had mentioned, I guess the difference between when you're hand packing and the machine packing, and then the other one that seemed like it's obviously more dense. I don't know if you misspoke, but you said that the second one was more dense, or was that?
Oh, here?
Yeah.
What, this one?
Yeah, you would say it was more void, right?
Yes,
Okay.
more void space.
Okay.
So this 70% void space is the targeted void space. So this is the void space we were targeting to fill. So so here's my box, right? If 60% of this is filled and 40% is empty, I targeted 70% of the 40% to fill with nanoparticles. And this is what I got.
Okay.
But yes, this is what was printed. So additive manufacturing has a world of capability, right? So what was printed, this is very nice and smooth, etc., versus what we had to do to simulate this printed. Because we're not at the point we want to just go putting nanoparticles in the binder and having the machine try to jet it out. Because there could be clogging, there's the chemistry we're working out with whatever nanoparticle you use with the binder. And so and plus, because we're working with a company, we're under a research type heading, but we don't want to just go tear up the equipment because they actually still use that printer for work at ORNL with some of their partnering companies.
Was this research actually done at Oak Ridge?
Yes. So this research is actually done at the manufacturing demonstration facility. And so the MDF, which is what it's called, their goal is to equip or enable manufacturing here in the U.S. so that we can be more competitive. Because as you know, manufacturing has suffered within the past years with it going across and overseas. And so what they're trying to do is bring science to some of our manufacturing companies that still exist here and try to make them more competitive on a global scale. And so at the MDF, they have multiple printers there. And so binder jetting is one area of additive manufacturing, but you have, what you would see years back with additive manufacturing is a lot of the prototyping. So a lot of companies use it for prototyping. So if they're trying to look at a model and see how it looks spatially, they may print it with some type of polymer, and then not necessarily use it, but maybe take measurements and all kinds of stuff like that. But we're trying to get to the point where I can print, really not a nut or a bolt, but I can print. So if I had a machine that's aged out and my manufacturer of the machine no longer supports some of the components, I can still be able to operate this machine because I can print whatever component that broke. And so this has industrial application and use outside of just a research atmosphere. But the thing is, we're trying to get more industry, we're trying to get industry to adopt additive manufacturing outside of a prototyping mindset or framework.
So I get that one of the goals is to get increase the density, I guess, to make it stronger
Right.
product. But are there other applications where you don't want to increase the density, where you're just fine with the lightweight or something like that?
Yes, so at Wake Forest, in their Center for Regenerative Medicine or something, there's research that shows that they use additive manufacturing to create scaffolding for bones. And this probably touches a little bit more with the bio folks in the room, but they use it for scaffolding. So that is an area where you don't want a high amount of density because you're building a scaffold for your body to use for it. If I'm building a leg bone or, I don't know, bone in my wrist or something like that. And so they do use it for that, where you don't want a high amount of density. So, and there's a paper out for that. You just Google Wake Forest, bone, something additive manufacturing. But I did read that article. So that's an area where they don't want high density. But we do, because we're trying to use this for industrial applications.
Any other questions? Okay, thank you, Alta.